So the first experiment says start with something we've done in the first semester. So go to your y equals. Go ahead and push y equals. And when you push y equals, yeah, whoa, things look pretty different, right? Instead of y equals, like y1 equals, y2 equals, y3 equals, it gives you x sub 1 with a t and y sub 1 with a t. So this is a little bit different than what you're used to. This asks us to make x 5 cosine t and y 0. So 5 cosine t. Hey, did y'all notice that? Did you guys notice that your input variable is now a t instead of an x? Okay, that's because you're in parametric mode. Y would be 0 as mentioned. It does ask you also to highlight the slash on the left. And I don't remember if you got to press enter twice. You got to press it a couple times. I basically want you to get right there. Oh, that's right. It opens up a little bit of a different screen. Instead of a line, I want you to toggle over to where you have like a ball, circle, open circle. So these instructions are a little bit outdated. Just get to the place where you've got the little O, and then hit OK. Okay. So we all in the same place? Yes? Go ahead and hit graph.
That's awesome.
That is,
Change your 0 to like a 1.
yeah, I'm like, I have a trace.
You can have the ball leave a trace or a little breadcrumb trail. So I'll hit enter or I'll hit graph here. Oh, I got a bunch of stuff going on there. Let me turn this off. Step plot off. Graph. About zoom 6. When you say go straight to trace, what are you talking about?
I was doing trace is just like, all I was doing is I was just trying to see if there was actually a bump out there.
You can, yeah. So what you can do here's something to think about. So let me go back and change this just a little bit. So I'll go back to my y equals, and I'm going to change my 0 to a 1. This will get it off the x-axis. And then instead of just a ball or circle or whatever, I will go with ball with line. This will leave like a path where the ball went. So if I do this and hit graph, now you can see on mine it's leaving basically breadcrumbs where the ball went. Does that make sense? Yours is what? Yours is not moving?
What's your replacement?
Oh, it's because we're in the woods.
Oh, because I'm in the previous.
Oh, yeah, I was in the green.
What did you make that?
That's right, I just need to go to
I need to do it whatever I want my
Okay, so guys, it says here in your instructions, it says to mess around. Well, it says set your window. Let's do the window right now. So did you all do that? My window is different. So my window should be T min 0, T max 30. There's something called a T step in there, which we'll talk about. But I'm going to go T min from 0 to the max 30. Watch mine for just a second. Watch what happens. So hit graph, and watch the ball go, and it stops right there. Okay? Oh, it's still going. Mine is, okay, I can see it on my screen. It's just a little bit laggy here. It's still going. And it finally just stopped. So I'm going to actually move mine back down. I'm going to make my y 0 again. And I want to say something. Will you guys watch this again? And I want to see if this sounds familiar. A particle is moving along the x-axis. And the velocity is described by blah, blah, blah. What is the position when time is 5? Isn't that what's happening here? Isn't a particle or an object just moving back and forth along the x-axis? We'll just stop there. So that's why I say kind of an example from first semester, we've been able to say, you know what? We want this object to just move left and right along the x-axis, and we can describe all kinds of things about it. Why was it moving, why do you think it was moving left and right, but not up and down?
Because there's nothing in the Y.
It's not that there's nothing in the y. Y is 0, right? So no matter where this object is, the y coordinate is 0. And if the y coordinate is 0, regardless of what's happening, isn't it going to be on the x-axis? So let's play around with this some more. You can do the same thing as me. Anybody want to predict what would happen if I made my t min 0, as it currently is, but I made my t max 5? So a lot less than 30. Any predictions? It would go back and forth less. Let's find out. So I graph this, it goes back and forth, and it just stopped. How do you think we could make this go back and forth for a lot longer time? Increase the what? Yeah, so instead of 30 or 5, what if we did t max 100? Check this out. It's just going to go back and forth, same path, but it'll do it for 100 counts instead of 5 counts or 30 counts. It'll just keep going back and forth. And this is sort of pointless, right? Because isn't it just tracing the same path? Maybe it's not pointless because it needs to go back and forth a bunch of times for some purpose, but it's not creating a new path by extending the time, because it's just pretty much 7 just going back and forth. Some other thoughts here? What's the maximum position to the right that this goes? Maximum to the right. What's the furthest right? What's the furthest left? What was the expression determining the left and right motion? And what's the amplitude on that? 5. You see why it went all the way over to the 5 and then all the way back over to -5? It's got amplitude, right? It's basically saying, hey, when you're way out there to the right, you have to turn around at 5, right? When you go all the way over to the left, you have to turn around at -5. So, what if I wanted this to have a much narrower path of moving back and forth? What could I do? Instead of 5 cosine t, it could be 2 cosine t. So we could go with that, no problem. Notice what happens here when I graph this. My t max is still 100, so it's gonna do this for a while, but notice how it now just goes between -2 and 2. Right? So I would encourage you to take a minute on your own right now, and as it says here, just mess around with the t-step. Go back to your window and see what happens when you do things to the t-step. And then we've already kind of played around with the t-min and t-max. So maybe go play with the t-step.
That's right.
Yes, ma'am.
Why does it work when it's at 0 and it's at 3 and 4?
You know why? You're probably in green mode.
I am doing wrong. Stupid physics, man.
Wow.
Blame Miss Wagner.
Would the T-step be,
Freaking Wagner.
what is the T-step?
What is the t-step? So let me mess around with it a little bit for the folks on the video. So if I go in here on my window, t-step for me is 0.13. I think that's the default. So if I made my t-step larger, so maybe if I made it, I don't know, 0.8. Now hopefully there won't be too much lag. It's probably, it might look like there's some lag. Let's see what happens here. So I hit graph. It's still going to go for that full 0 to 100, but it almost seems like it's kind of skipping around a little bit.
Wow, that's what it is.
Skipping around. So let me change the t-step again. So the t-step right now is 0.8. So originally it was 0.13, so what if I made it 0.01? This might be a little too extreme. So I went from 0.1 basically up to 0.8, and we got all this skipping around. So if I make the t-step a lot smaller, here's what happens. So notice there is not any skipping around happening really at all. And it's going really slowly.
How fast it like moves over the wall?
Kind of. It's not necessarily how fast it visually looks like that. I want you to think about this. Here's how I think about the T-step. The T-step is basically the time in between you or the object putting down a breadcrumb. Okay? So when the T-step is larger, like, I don't know, like say 0.8 or 1 or something, that means there's a pretty long time between you dropping a breadcrumb. So if the T-step was, say, like 1, that would be every 1 second. So it'd be drop it, drop it, drop it, another breadcrumb, another breadcrumb, another breadcrumb, another breadcrumb, right? So you're just getting like these kind of choppy points on where I am. But if my T-step is really tiny like this, when we change the graph a little bit more, you'll see it more starkly. That means that the time in between me dropping breadcrumbs is really short. So instead of what I just did, it's like breadcrumb, 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 over and over and over and over again. And so I kind of have to walk slower because I got to grab a new breadcrumb every time. But I'm dropping a bunch of them, so my path is very precise. You can see exactly where I'm going.
Okay.
Think of it like a GPS waypoint.
Frame rate on a computer almost.
Right. So like if I wanted to map out a path, to my desk, you know, I could drop a breadcrumb, drop another one, and it's going to almost look like this triangular thing. Isn't it going to make it look like I walked through the table?
Yeah.
Whereas if I'm constantly dropping breadcrumbs on my path, you're going to say, oh, actually, he kind of took a curved path to get back to his desk.
Huh.
And so the shorter the T-step, the shorter the interval between breadcrumbs. You'll get a much better look at what's happening, but it'll take longer because you're dropping more breadcrumbs. That's why we're still going to T equals 100. It's still going because it's taking forever to drop breadcrumbs. Make sense? Okay. Let's see here. I think that's about all I want to do with this particular one. You okay with that? This is the proverbial. A particle moves along the x-axis. Motion modeled by whatever, right? So what we're going to do now is we're going to graduate out of this world of particles being restricted to the x-axis only. And now all of a sudden they get to move around left and right and up and down all at the same time. So if you guys would, will you guys check this out, please? The way that you release the object to move not only left and right and up and down, but also up and down, is to make the y value, the y expression, something other than 0, or really something other than a constant. Yeah. So in my notes here, I had you guys do ln of t for your y value. I'm going to go back in and I'm going to make my window a little more appropriate here. And it'll go like 25 or something, and my step size will be 0.1. And I hit graph, and I can see this lovely shape going on here. It's kind of laggy, sorry. And now you can see that this particle is now free to move left and right. You see how it's still moving left and right? That part hasn't changed. You see how the furthest right it went was, so I left mine at 2 cosine. So it goes as far to the right as 2, as far left as -2, but now instead of just going back and forth, it's going back and forth and up. Right? Oh, you can make some pretty awesome looking graphs by doing that, yep. Wait, how do you do that?
My y is 7 sine of pi over 3.
Yeah, so you can like I would encourage you, this would be one of those moments, and I don't want you to do it right now, I want it to be fairly self-directed, but within reason, and we'll play around with this for a while here. like, if you had a bored moment, like, let's say, I don't know, you were on the bus heading to a game, or you're in a family car going somewhere, and you're just bored, you got your calculator, just start messing around with this and say, I wonder what would happen if I,
Sometimes I just have my calculator in the car.
you should. You totally should, as long as you're not driving, don't
Calculate and drive.
text and drive, whatever, we're talking about
Don't
calculating.
text and drive,
You're in a
don't
car, though.
rap and drive, you know.
Well, I just got
Can
Disney
you,
Plus,
can
so
you
my car
imagine if
rides
you
would
got
be
pulled
very
over and
different
the
now.
officer's like, hey, you can't text and drive,
The officer would be like,
He's like, I'm
nerd.
giving you a ticket just for being a nerd.
Weirdo, yeah, like, you're getting the +1 nerd penalty. That'll be an extra $80 on your ticket for being a nerd.
Yes.
So you can go back in and you can make your Y1 all kinds of stuff, right? I mean, you could go back in here and say, instead of ln of t, I want this to be. You want to do arcsine? We might have some domain issues here. Arcsine of t. Let's find out. What's it going to look like? Oh, that's it. We have some domain issues
Well,
probably.
you know what? Have to kill the goose.
So let's see here. What if we did?
Whoa!
Oh, come on.
I'm just
Oh, mine is like-
random stuff now.
I still don't.
I'm
Mine's
making
freaking out.
scribbles.
So let's do something that doesn't have domain restrictions. Like, how about e to the
Oh, let's do
t? E to the what? E to the t?
E to the cosine.
We could. It gets weird, probably. Weird is okay. E to the sine of t. Okay. Interesting.
It looks like
That's fun.
potato.
I
Let's
went
eat it
t
aside.
times tan 8t squared.
I'm just putting in random stuff.
Oh,
Let me see. I want to see what you do.
we made it explode.
I made an explosion.
Whoa, what is that? Let's see your equation.
Oh.
I did it.
E to the. Oh,
I'm doing your tangent of the cosine
Yo.
of the sine of pi of t.
yes.
Yo, Nick, check this out. Put this in your calculator. 13 tangent of pi over 2t squared.
I think this is exact. Your x, right?
That was my x. And then for the y,
Oh.
Hang on.
Wait,
He was putting
13
there
tan
for
what?
y.
13 tan what?
pi over 2 to pi over 2t squared.
Over 2 and then t
Pi over
squared.
t squared. And then for your y,
Whoa!
for your y, do the same thing, but put that expression and raise it all to the e. So e
Is
to the
that the one
tangent
we
of pi,
said, or
pi over
no?
2
No.
t squared.
I was a great
You ready for this one, Elizabeth?
This is fun.
This is kind of what math is. Sometimes math is just like.
It's ugly. It's really ugly.
Crazy.
Oh my goodness. What did you do, Raven? The ball is bouncing around everywhere.
Now we're gonna take it all.
Oh, you made it.
And divide it by ln of sine.
Number or random integer? Yeah, so it's gonna be different every time. Isn't it? That's awesome. What's your t-step?
Okay.
Okay.
I don't think we're gonna get much more exciting than making that as well. So I'm gonna stop.
I don't know, Aiden put in a random number for his Y value. Like the random number generator.
What? Oh, you can factorial. Okay.
That's a pretty, look at that, that's a pretty wacky graph.
Wow, that's something.
It's like fractals. This is
Wait a
whack.
second. Can
I want to get how do you get patterns? Patterns. Yo,
What do you mean?
he was getting like all these like there was like symmetrical.
What did he put in?
I don't know. He wouldn't tell me.
Wanna share my
Guys, my favorite one is still the formula. It's a good question.
Can I see your equation?
Graph first, but it's
Seven.
5 cosine of t, and then y is
Whoa, that was
7
whack.
sine of pi over 2.
That's an hourglass.
It makes a little
I made an hourglass. That's pretty.
Nice.
What? Wait, what? You made a legit hourglass. How the heck did you do that?
Sine.
That's really, I mean, Logan was talking about how do you get patterns.
Guys, look
Like,
at that.
that's a pattern.
That's exactly what I'm talking about.
Oh, that's the one that showed Logan. That's I think what was that? It was cosine.
The X
Hold on.
is 5 cosine of t and the y is sine of pi over t. Or 7 sine of pi over t.
Okay.
Yeah, it makes sense.
Isn't that fun? Is that cool?
What if I change this tangent? Let's change this tangent and make it 6.
Whoa, what is that?
Whoa, whoa, that's sick.
What is that?
What the what? Look at that. Dude, hold on.
I just put it in the mental.
That's next level.
Whoa.
So they're doing like my
Next level.
4-year-old son.
Look at that. That is so cool.
It's
That looks
actually
like
a
that
little
looks
more of a
3D.
package.
Hold on a second. Yeah, that literally looks like 3D. That looks 3D. Look at
That
that.
does look crazy.
Look at that. Mr. Anderson, what did I just create?
Look at what I just created, look at that thing.
Wow, those are art hours. Is there tangent involved?
I just created the Halo sword.
Whoa.
It's double-sided.
Nice, dude.
Oh.
It's really narrow, but like,
Yeah.
it's kind of, it's got the like
It's got
that.
something to do with like, if I make this 8, does that make them more? Yeah, it does. That's cool. That's,
Wow.
there's like a wall to it. Like the sign.
Wait,
Wait, what if I make this like,
And Julia and Meg and Santi are missing out on play day.
literally the day we're just play.
Playtime.
And
Playtime.
it's almost a full rectangle.
Yes, you did. What made that? That's got to be sine and cosine stuff, right?
I did 5 cosine of t and 2 sine of the absolute value of t squared.
I want to see. Good job. Whoa.
And you probably a huge T-max, right? Because it's color in. Oh, 500. You should zoom in on that and see what it looks like.
Nice, dude. Sick. Whoa, that's weird.
There's. Wait, does anyone else know like the Treyarch symbol from Call of Duty?
Well, you're gonna-
How would you make that? That would be crazy.
I don't know, we'll figure it out.
I'm one of them playing understanding right now.
Oh, cool, but it's
It's
not.
just math, dude.
How
So,
do you
is
make
this
this
T-
fun shape?
So is this,
How do I make a heart?
How do you make a heart?
One time Mr. Blake taught us how to do it, but I don't know.
In Poland? It's in Poland.
Yeah,
Yeah, that's
The lemon
cardio.
is,
Yeah.
it was fun.
So let's see here.
we do 2 semicircles and a parabola.
Polar is parametric. The parameter is just different. Parametric, a generic parametric, the parameter is time, and in polar, the parameter is different. They're both parametric.
I created a line.
How would you make a heart?
Oh, that's granite. That's much more interesting.
Let's take the tangent
Whoa.
of 1 over.
Oh, whoa.
So, do this. Okay, so like maybe do like your x would be like sine of, say like sine of t perhaps. Yeah, sine of t. And then y, let's see, we have to go. What would work? Go up and then down, they have to go down, sort of increasing the grade. So,
I want to see, but don't spoil it. I want Mr. Anderson to see it
Like,
in his math.
let's see here. So what if you did,
How are you doing this?
okay.
What are you? You're just like a generator.
So,
Thanks.
we could do,
I want to graph 21.
so how about like,
This.
negative, let's see here. Let's see here. Like negative 2q.
Oh, that'd be
That's the washer method.
Close, actually. It's like a scheme. It's a scheme. So maybe if you did like,
This is a scam.
Already, not see that,
like a 0.1 plus Sam.
Wow.
Wait,
Hold on, let's make.
Let's make the steps
No,
longer.
no, make
Oh,
that.
Yeah, let's make it, let's do it.
Sam, I just gotta say, Sam, you're so much fun, dude. Like, you're so going against the spirit of math. Spirit of math is, I wanna figure it out.
I wanna see heart.
The spirit of weak sauce is, I'll just cheat my way through it.
Stop cheating, it's using a resource.
That's just-
Said every
that's
cheater
just
ever.
semantics. That's just semantics.
Total good shot.
Have some pride in the idea that maybe you could figure it out.
Wait, we're gonna do, and we're doing probability. That's probability of that doesn't happen.
No probability.
How much you making? That's not interesting.
That just kinda sucks. Well, I actually figured it out. Hold on. We're getting up there. One, two.
Oh, that's
Oh,
pretty cool. That was a lot of
That's sick.
two-dimensional.
how did you do that?
5% T and then 5 sine absolute value 60.
Okay, so hang on.
Oh.
Hey guys, pause your messing around. I want to bring up an issue that always gets brought up, but nobody's brought it up yet. It doesn't always get brought up, sometimes does. Somebody will often say, hey, I've got a problem with this because if you take a vertical line and you take that vertical line and you move it over the graph, doesn't this graph fail the vertical line test?
Everywhere.
Well, it's over time, so it doesn't really matter.
Well,
Because the particle's not in.
this is where we get a little more technical, right? So if I were to ask you, based on seeing the graph like that, if I were to say, is y a function of x, what would you say?
No.
Definitely not, because you can see for pretty much all the inputs, there are two outputs. But both are functions of t. So in other words, if y is a function of t and x is a function of t, that at any given time, the particle is only in one place. Right? There's only one y value and x value for
Oh.
any given value of t.
Yeah.
So you can't say that about y in terms of x, but you could say that y in terms of t or x in terms of t. So these are still functions, right? Because sometimes you'll hear these referred to as parametric functions, and people will object and say, well, the vertical line test thing, totally get that. So this is where we're going to use a little more precise language when we talk about is y a function of x, is x a function of t, is y a function of t. Just like we'll later on when we get to polar graphs, right? We'll say r is a function of theta. So unless we're talking about a lemniscate, for every theta there's one r, right? With a lemniscate, for every theta there's a plus or minus r. And so you gotta either pick one or the
Go
other
back to Mr.
or
Blake's class.
do both.
I was in Mr. Brooks' class.
Nick wasn't.
That's
I
me.
wasn't in.
Let's see here, what do I want to
That's
do?
embarrassing. I made a sideways sign.
Wait, how did we make that held function again that we did that gave us pi?
What'd you get?
4 over, or 1 over, 1 plus x squared, or,
Ooh.
Okay.
yeah, 1 over 1 plus x squared.
Ish.
Like
But
the
they all-
microwave?
Yeah, they all ended up
Like sound
condensing
waves?
into one.
Like a sound wave?
No.
Whoa.
Turn it.
Back and forth we go, huh? This sine was taken over that, wasn't it? That was all about sine, going up and down there.
Yeah, I'm good. I'm just sometimes you just start to hit, you know?
Stretch them out.
Stretch your hips. Your hips are bones.
No, they're joints.
Ha!
The hips
Logan.
are joints?
Yeah.
Well, you know
Yeah,
what?
that's why
How
you
is
sit
it
in
developed?
splits.
Your
My,
pelvis.
my hip doesn't stretch.
My hip does. My hip stretches an abnormal amount.
That's why you're a palms girl. I would be a palms girl too if my hip could stretch.
Amongst other.
Most other qualifications? I would be a palms girl, but I don't meet 50% of the men, so.
You know, technically boys can try for moms. No
Not
one does.
valid. Well, I worry.
At Valley? I thought it was not 11. Or was that cheer?
Hey, guys, we're gonna do one of these by a paper pencil, so if you would, please take your calculators, put them away. That was fun. You guys did a great job playing with us, and we'll probably do that, we'll probably start, Monday, again, with a little bit of that playing around with the calculator, just to hopefully get Julie and Meg and Santi into that as well. Because if they're watching the video, they just watch you do it. Maybe they just do it on their own, or they watched me do it. They didn't actually see all the stuff we were talking about. We were like, whoa, that's interesting. And, wow, that's cool.
All they do is, whoa, look at that.
Whoa, yeah. So it might be nice for them to try some of
I
that
was
too.
feeling on Sam for a minute, just like.
So let's fill in a blank or two, do a graph, and that'll probably be our day or close to it. We'll just see how it all goes. So parametric equation is an equation in which both x and y depend on something. And for us in this generic mode, they're both going to depend on t, which we will typically refer to as time. And conveniently, when we get into vectors, we'll deal with those in a parametric way as well. So t will still stand for time when we get there. So sometimes these will fail the vertical line test. Y is not necessarily a function of x, like I just said. So I've got several examples where we're going to graph these. We're going to put down our own breadcrumbs. So I've kind of set you up for this with a little table off to the right, parametric expressions for this equation. When we're done, we're going to try to eliminate the parameter and see what happens when we eliminate the parameter. The parameter here is t. We're going to try to eliminate that from our equations and just see what happens.
Are there going to be some where we can't?
There are going to be some where it's like maybe you can't, or maybe it's just, well, definitely there will be some that you can't. Others it'll be like, what's the point? It's going to take you longer to do that than just deal with them as they stand. So notice it's a 3-column table, right? Because x and y both depend on t. So you're going to be plugging in a t value into your x input and a t into your y input and seeing what comes out. I'll be doing that up here while you're doing it there.
It's really bugging me that on the coordinates it's -1, -2, 0, 1, 2.
I agree.
Oh,
It's out of order.
that's a little bit weird. Sorry about that.
It's okay. I forgive you.
That is a little strange. I don't know how that happened.
I'm gonna be honest, I did not notice that.
I didn't notice that until you said something either.
But it makes my graph feel like a lot more.
Isn't that terrible? All right, let's graph her.
Should be 1 plus 1. Right, 1 minus -1. Funny. 5, 1, 2, 3.
It's no fun.
Wow, this classroom is so much quieter without Meg, Santi, and Juliana.
I hope they hear that on the video.
He probably did. It's got a pretty good microphone.
Still love you guys.
Speak for yourself. Sounds good.
So I think I've got the table built, and well, we have totally different looking graphs.
Yeah, I have the same as you.
Oh, no, I have the same as you.
I have the same.
I think we're just.
I'll take one of the extra notes.
That's why. Oh, you did it in green.
I did it in pen, man.
Yeah, but you did it in green.
My self-esteem.
Let's
is really
like
low
I
right
would say
now.
just like restart or something. I want to save those for other days, like for our other folks. Plus, if somebody
I hope someone watching the video messed up too, because that's just really embarrassing.
could have happened. Hey, so it's interesting that you all brought up, or some of you brought up the time progression being a little bit odd, right? Not progressing from smaller to larger or larger to smaller. There was like a little jump. I would really want to redo that table, to be honest with you, because when we graph these, what we will typically do, and I will say we'll always do this, is we'll connect our points oops. We'll connect our points, and not only will we connect our points, we want to give the direction of motion. And so for this one,
Oh no.
we draw little arrows, or just draw one little arrow here, indicating that, assuming we get our times in the right order, we're going kind of in a from upper left down to the lower right pattern of motion. We don't want to give those little arrows there. Another thing that's kind of interesting about this one is it looks very linear, does it not?
It's because it's a line.
It looks like it could be a line. So one thing we could do to confirm or deny this is to put this into a more familiar form. And like Jack asked about, this is not something that will always work, but in this case it'll definitely work, and that's called eliminate the parameter. So the way you eliminate the parameter is to use substitution. So what I could do is I could take my y equals 1 minus t, and I could solve it for t. So it would be 1 minus y, right? Equals t, 1 minus y. And then in my other equation, I could replace the t with 1 minus y. So now it would be x equals 2 parentheses 1 minus y minus 1. Do a little distributive property, so it'd be x is equal to 2 minus 2y minus 1. So it'd be x is equal to 1 minus 2y. This is looking very linear, is it not? In fact, what I could do is take it all the way to slope-intercept form. So it'd be x minus 1 equals negative 2y. So negative 1/2 x plus 1/2 equals y. So look at what you have on your graph, and you can look at what I have. Does it look like the slope of that line is really negative 1/2? Depends on which one you're looking at, right? On my screen, at least.
Yeah.
And then do you see how the y-intercept is some little fraction between 0 and 1?
Yep.
So it's like slightly bigger than 0. 1/2.
Crazy.
Makes sense.
Math.
So,
How do you draw it?
how do you draw it?
How do you draw the graph? How do you plot the points?
So I used my data points out of my table. Like my first point was negative 5, comma 3. And then my next point was negative 3, comma 2. And then negative 1, 1, 1, 0, 3, negative 1. So I'm just looking at that yellow part of the chart there, saying that is the same kind of table that you would have made in Algebra 1. Right? You got a bunch of x's and y's, you plot them on your graph, and then you see the pattern. So my point here with asking this, you can see a little question there at the bottom. Does this make sense with the graph? It should, right? They're both lines. The y equals negative 1/2 x plus 1/2. That's slope-intercept form. I've got a line up there. Does this make sense? So somebody could ask a question, why would we bother with parametric when we could have just done this? You're actually going to find as you move through calculus, especially when we get into like 2D motion, 2D vectors especially, parametric is so much easier. It's not even close. And then, if there's ever a time when you take a Calc 3 class, almost everything's in parametric. Because it's easier to break it into 3 chunks, all in terms of t, versus trying to slam it all together into this one ugly thing with x's, y's, and z's, if that makes sense. And so, yeah, if you do move forward in math beyond this course, you will definitely see a lot of parametric, sometimes in terms of 2 variables, sometimes in terms of 3, if you do take a Calc 3. Okay, sometimes 4 variables, all kinds of different stuff. Yeah. Okay, so let's see here. Let's play around with this next one. We'll just kind of see where we go with this. Yeah, this is worthwhile, and the table is in the right order. So maybe this will work a little bit better. So x is equal to,
It's pencil time.
hey, can you already tell this is definitely not linear?
Yeah.
What tells you that?
Yeah.
Square roots. Yeah, the fact that you got a root t for your x
Maybe here's primary.
means it's not linear.
Dang, that's kinda cool. Sweet, let's get them going. Great, running out of room.
Yeah, I think this one might drift off the graph.
Well, I would do a scale, but I'm not, weak.
Hey, you calling me weak?
Yeah,
No,
Yes, absolutely.
well,
without a doubt.
considering you're,
A golfer.
well, that's,
I knew it was gonna
that's not
happen.
where I was going, that's not.
Guaranteed it was gonna happen.
Good point, but I was gonna,
I mean, you're not.
Not saying it was.
Okay, Aiden.
I'm just
What
kidding,
sport do you
okay?
play?
Play a sport.
Well,
Hey, at least we can all agree on one thing. We're not Michigan fans.
oh, yeah. It's like up there, guesstimate. That looks pretty, that was pretty good, Jack, nice job.
I love you.
I love the self-affirmation.
I was going to say, when you have yourself with you, you don't need anyone to encourage you.
I tell myself jokes. I make myself laugh. I don't do anyone else.
You sure?
He says
Do you
that.
ever say a joke and then have to tell yourself that was dumb? Do you
Constantly.
ever give yourself a courtesy laugh? I mean, that's the ultimate. Like, ha ha
That's
ha,
the way
nice
to grab it.
one, weak joke.
Alright, that's equals.
I mean,
Um,
it's a joke, but
You guys getting something like that? I hope you are.
Oh, I did it right. Oh.
Oh my gosh, why are
It's
you
kind of the
so
goal.
excited?
Oops. Even golfers are right every now and then.
Boom.
Oh, okay, Mr. Anderson.
Come on, let's just have some fun here. It's okay.
Wow, I just did not expect it. I respect it. But like, oh man, that went from 0 to 100 in a hurry.
what do you call it?
You only joke like that with people you like.
Oh, thanks, Mr. Anderson.
It's the truth. If you don't like someone, you're just like, I don't want to make them mad.
Hey.
I'll just leave it
Good
alone.
what?
I won't say that.
I appreciate a good joke.
How about the Logan?
Logan.
So did you guys include the little arrows indicating that it's kind of going up and right?
I am.
That was the direction that this particle, if it were a particle, is going. Eliminating the parameter here is kind of interesting. You can actually do this pretty quick. If I took x equals root t and I squared both sides,
Yep.
I would get x squared is equal to t.
Oh, so it's T squared.
And so then y equals, oh my goodness, that should look familiar. Didn't that look sort of like a parabola when you plotted those points?
Just a little bit.
So this x equals root t and y equals t plus 1 is actually the parameterized version of a parabola. Okay?
With motion.
Yeah, so like with motion. Of course, how do you guys think that you would get the left half of the parabola? Because we only get the right half.
You'd have to
Say
do
again?
the whole,
Negative, not negative, no, not negative root t.
No.
That would
you'd have to do,
that would sort of work. What would be a different way? Because you just get the negative x. So how would you get? Let me say this. How would you get the whole parabola
Plus or minus root.
Or negative x equals.
without touching the x and the y,
Wait.
without changing the x and the y at all? How could you get the whole thing?
was the
Imagination.
opposite, was that what it was?
Just think it
I
up.
don't know.
No.
I don't think,
Reflected across the line.
yeah, well, great.
Do you go
Good
to
idea.
T
Well,
and
yeah.
equals negative
I
one?
mean, we're
It's-
trying
Oh, what if the t values went negative? What if we went back in time?
Like,
can't
but then
take
you'd be a
the
negative
That's
square
great, but then you're
root.
taking
Oh, then we get a negative square root. What do you
Then it's
think? What could we do?
imaginary.
Be an imaginary square because that's not going to work
You
either.
need a complex graphing plane.
Yeah. If we had the complex plane, so maybe there's not a way to get the whole thing, right?
There isn't.
You can.
You can't do such a thing, parametric.
well, because
Okay, but-
time doesn't go,
What?
I mean, it does.
So you can actually have negative times. Basically, it would be the time before a certain reference point. If that makes sense, you could say, hey, 2 seconds ago could show up as a -2.
Time did not exist before
Maybe
that.
small
Before then.
Well, I think it probably
thousand
did, but you never know.
bottom of-
Yeah, so I don't really think you can get the other half. So I think the way that you would have to get it is to consider both the plus or minus version of the square root.
How's it feel, Logan?
hey,
Okay.
he's not a golfer anymore.
Hey guys, so
I quit.
the point of today, I want to make sure you understand the goal of today. Listen, hey, you're going to leave here in just a second. Make sure you get this. The goal of today was to get you guys somewhat familiar with parametric relationships, parametric functions and graphs, where they come from, what they might look like, a little bit about the calculator as far as what the calculator could do to help you. We will spend all of next week talking about parametric graphs and calculus. We'll talk about the slope of a parameterized graph, the second derivative, so on and so forth. We'll spend Monday, Wednesday, Thursday on this. Well, Thursday will be kind of a review. Friday's your quiz on that. So, all right. I think we're good. Have a good weekend.